So this is the site of MeshLab, and you go to downloads. Now there are different binaries that are available for you. You can either directly install from Snap in case of Linux. For Snap, it's pretty simple. You can directly run the command for installing via Snap. It's just snap install uh, MeshLab, and you can directly install it from the Snap store as well. For Windows, there's a binary that you can download and install, and similarly for Mac. So once you have downloaded MeshLab and the meshes that I have provided, just uh, go to the directory where you have downloaded the mesh and simply drag and drop the mesh in the MeshLab. So firstly, let's look at the bunny OBJ file. Is the screen visible? So
Yes.
this is something that you'll see in case of bunny mesh. So as you can see, when you load a OBJ file, you can see the vertices and the faces. So these are the basic properties that will be helpful for us. Along with this, now we are going to analyze it a little bit. So what you can do is you can go to Windows and go to click Layer dialog, and here you can see when you click on a object, you should be able to view its properties as well. So this I is for enabling or disabling a layer. If you guys have used Photoshop or some image processing tool like that before, this is a common feature that is available to you. You can edit things layer wise and select them layer wise. So when you click on it, you can see all the different properties that are visible to you. Along with that, there are several options that you can do. So if you go to render, you can actually see the different information that is available to you. You can directly print the face norm, show the face normals. So essentially, all these blue lines that you look here are the normals from the point on the surface. So these are the normals that you can directly view using the render option. So these are the face normals. Similarly, you can also render the vertex normals. These are the per vertex normals that you can use. I hope all of you are familiar what normals are. Normal is just a perpendicular vector from the point on the surface. So these are all the normals that you can view. Similarly, you can view the face normals. Then you can see the vertex quality histogram, the face quality histogram, and so on and so forth. So let's begin with some basics. Just give me a sec. I'll also So how do you define the quality of a mesh? Is through its properties. So we'll briefly take a look at the some of the properties of a mesh. So right now we have loaded an OBJ file here, right? But we don't know how an OBJ file actually stores information. So what you can do is open any text editor and try to load an OBJ file there. So for example, I have, for example, I'll use Sublime Text or Simple Text Editor. So if you open an OBJ file in a text editor, you'll see that these are the properties that are actually being loaded. It's a simple text file, but the way it is, there is a specific format to it through which it loads the information and displays it on their screen in the machine. So all these VNs that you look here, so VN is essentially the vertex normal. So this is the normal vector pertaining to every vertex. Similarly, this is the vertex, and this is then so on and so forth. So these are all the vertices and their vertex normals. Similarly, if you scroll a little bit below, you will notice that these are the faces. So faces are nothing but the indices of the vertices that make up a triangle. So here what we see is these are the edges essentially. So from vertex 7203 to 720. So all these are making up the edges. So there would be an edge corresponding to 7203 and 7204 vertex. Similarly 7204 and 7308. So these are the three vertices that make up this triangle. And similarly you have some more information. If you at the top you can see all the number of vertices and the number of faces. So there are like 34,000 vertices and 69,000 faces in this bunny mesh. So the quality of a mesh comes from different things, from different attributes. You can judge the quality of a mesh from the kind of surface it has, from the kind of triangles it possesses. So in case of a mesh, you have different attributes. You have vertices, you have faces, and you know that there are different kinds of meshes even. So a mesh is essentially a collection of triangles, right? So, but it can also be a collection of quadrilaterals. So you call that a quad mesh. So either you can have something like this where each simplex is a triangle, or you can have something like this. You can even have a quad mesh consisting of 4 points. So instead of triangles, it is consisting of squares essentially. However, we go for triangle mesh because even a quad mesh can be broken down into two triangles. So you have a vertex v1, v2, v3, and similarly here. So how you can represent them? You can represent them using a vertex list and a faces list. So each face consisting of the vertices that make up that face. Similarly, you will have another, in this particular case, you'll have one triangle which will be v1, v2, v3, and another triangle v2, v3, v4. Now you can represent them as lists and matrices. So when we go into the application part, we'll see that they can be represented using NumPy arrays pretty easily. And also note that even though we are looking at 2D figures here, all these vertices are in R3. So each vertex has a x coordinate, a y coordinate, and a z coordinate. So essentially this list would be something of size n cross 3, where n is the number of vertices and 3 are the coordinates essentially. And similarly, the face would be a matrix of size n if for number of faces times 3. Because here we are not directly referring to the coordinates, but simply the index of the vertex. So we can similarly say that this is vertex 0, this is vertex 1, this is vertex 2, this is vertex 3. So we can simply store the index that helps you save some space instead of directly saving the coordinates of each point in the face. So my face matrix would look something like this: 0, 1, 2, 1, 2. So this is how you'll be representing it when you are representing it as a tensor. By tensor, I mean a multi-dimensional array or a matrix. There are different operations that you can perform with MeshLab. So now you see that there are some artifacts in this mesh as well. So you see that there are some holes in it. right? So holes, essentially what these holes make it, holes are a problematic case because here then you don't have a continuous surface. You have a discontinuities and you would want to remove these so that the operations that you can perform on the mesh are smooth. Yeah. So there are different tools that you can use here. So this is a hole filling tool that is available to you. So you can see that it has already calculated some of the potential holes in the mesh and marked for you. So you can directly select them and you can fill these holes. So once you fill, you can see that now it is a continuous mesh and it is much more easy to perform operations on such meshes than the meshes that have discontinued. Hole filling is one of the basic operations that you need to perform to improve the quality of a given mesh. Another thing that determines the quality of the mesh is the kind of triangles you have. So as you know that we have different kinds of meshes. So meshes are just triangles that are interconnected with each other. So now there can be different qualities of mesh. You can have semi-regular meshes, you can have regular meshes, and you can have irregular meshes. So what essentially an irregular mesh looks like is that the angles that these triangles have are not regular. So in the best case, what you would want is that all these angles should be, you need to have an equilateral triangle to have the best given property. So all these angles should be 60 degrees. And in the case you have a 60-degree angle that this particular triangle this particular vertex subtends with the adjacent edge, is that in this particular case, if you cover a complete circle with a triangle fan, you'll have exactly 6 triangles in a given triangle fan because simply stating that 360-degree divided 60 degree, you'll get 6 triangles. So essentially, 6 triangles would compose your triangle fan in case of a regular vertex. In case this vertex is not regular, so that means that this particular angle can be either more than 60 or less than 60. So essentially, the number of neighbors that this vertex will have would be non-uniform. So that is what governs the quality of a mesh. So let's take a look at the edges even. So if I highlight the edges, so you can see that in this particular case, there are some locations where you can see that the triangles are bigger, and in some positions where you can see that there are gaps. So like along this point, along these points, you can see that these triangles are bigger than the rest of the triangles in the surface. So this is an irregular mesh. Essentially, the vertex at this point would not have a uniform neighborhood. And even if it has a uniform neighborhood, the triangles would not be very uniform. So like if you look at this surface patch here, we see that it's a highly uniform surface, whereas this surface here is not uniform. You can even select set of vertices uh, in your mesh. So I can directly select vertices. I hope it's visible to you. So these red vertices are the selected vertices. So this is about the uniformity, and you can do different operations using MeshLab. I would advise you to explore it even more. So you can directly select points belonging to a particular plane. Similarly, you can even delete a set of vertices, and you can select a set of faces. So essentially, I can directly pick some set of faces that are lying in this particular region and even delete them. So all these operations are pretty quick with MeshLab. Another important set of operations are the transformations that you can quickly do. So you have directly transformation operations that are available to you, like move, translate, rotate, scale. You can directly move a given plane along an x-axis. I have moved it from the, yeah. So you can simply translate it, and similarly you can rotate it, flip it, and directly export it as a new mesh. So all these operations that you're performing while transforming are being applied on the vertices of the mesh. I hope transformation matrices are clear to you. In case they're not, so essentially what we do is that for a given set of vertices, we multiply them with a transformation matrix to obtain a new set of vertices, v1 dash, v2 dash, v3 dash. So this is a simple matrix multiplication. So for example, if you need to scale a matrix, scale a set of vertices, you can simply multiply them with a scaling matrix, and you'll get something like this. So you'll get Sx v1, Sx Sy v2, Sy Sz v3. I hope this is clear to you. In case it's not, just let me know. If you want me to slow down, then also let me know. We have plenty of time and we don't need to rush. So, is this part clear? Okay. In case of doubts, feel free to ask. So, this is, yeah.
This is really what type of transformations that we get after doing this linear transformation or matrix multiplication.
So, right now I just performed an affine transformation. These are part of rigid transformation. So, essentially, you're not changing the distances between the vertices, you're just moving them along. So, this is one of the properties of rigid so we are only performing rigid transformation. You can perform non-rigid as well. You can perform shearing and such other transformations as well. So depending on the kind of matrix that you formulate, you can perform different uh, operations. So a rotation matrix would consist of different set of operations along these vertices. Similarly, if I need to perform a translation, I'll be using a different vertices. But overall, that's a rigid transformation. I'm not changing the inter-vertex distances as such.
So basically, the object file that you have taken input on using by clicking and translating with the mouse. Basically, there's a matrix operations going on in behind to change the
Yes.
vertex according.
So right now, the kind of operation that is being performed is not on the mesh, but on the kind of view. So right now, there is a camera in place that is actually viewing. So right now, when I move my cursor, I'm not essentially moving the mouse. I'm moving my camera to view the mesh from different points. So there is no editing in the mesh that is going on when I move the mesh like this. However, when I perform some filtering or some operation using these operations here, transformations, at that point, I'm actually performing operations on the vertices. Right now, when I move my mouse, I'm just changing my viewpoint. I'm not changing the mesh as such. I hope it is clear now.
Yes, and during hole filling, basically you are adding new vertices.
Yes, yes, yes. We are closing these gaps. So we see so there are different algorithms that you can use for hole filling. So essentially, you can simply extend these triangles till the time they don't collapse in the middle point based on some heuristics and some energy function along which you will minimize. So that is hole filling essentially. Hole filling is important because let's say I want to define an operation, but then points are missing here. They're discontinuities. I would not want that. I would want a smooth operation to be performed. So you can even perform smoothing using MeshLab. So now if you look at this, the mesh has become more fine, has become more smooth as a surface. So there are different filters that are applied in different patches on the surface to ensure there is smoothing. So perhaps in later sessions of the workshop, you will be looking at smoothing operations as well. I think Professor Kaushik is going to take one session pertaining to that.
Is this smoothing because of so that the surface remains differentiable? That's why we perform smoothing, or to generate a better texture.
It's to perform better texture. We want a continuous surface. Differentiability is something different because you have a discrete surface, so it might not be differentiable. However, you want a continuous surface that it is defined at every position. So let's look at the case of non-manifold. So another thing that defines the quality of the mesh is the manifoldedness of a mesh. So manifoldedness ensures that the operations that you perform later on are well defined. So basic example of a non-manifold is when a vertex is joining two triangle fans. So that is a non-manifold vertex. Or you have a triangle that is intersecting another triangle, as you can see in this figure. So this is a non-manifold case because there are two directions essentially in this particular case, right? So you can either move upwards or you can move straight ahead, and you don't know how you're going to define the movement along this particular edge. So this is non-manifold case. So this is also another example of non-manifold case. If you remove the upper triangle mesh, then it becomes a well-defined surface. You can move in any of the trees below directions. But the existence of a non-manifold vertex is not advised because later on when you use finite element methods or define differential equations, you get niche cases in this particular thing. So you want to you would want to avoid such bottlenecks. So simply you can there are different algorithms that are pertaining to creating a manifold mesh out of non-manifold. We are not going to talk about those algorithms in specific, but we are going to see how we can directly perform such operations. So now I guess it is time that we move on to the next part of the workshop, and we start with libIGL. So firstly, in order to, I hope all of you have installed libIGL. If you have not installed libIGL, then firstly activate your Conda environment. I hope you guys know how to activate Conda environment. In case you don't know, so for example, you can type Conda activate. Let's say my environment name is IGLM. So just write the environment name and press enter in the terminal. And once you have this ready, I would want you to install Jupyter. Conda install Jupyter. I'll just paste this command in. So once you are done with the installation of Jupyter, let me know. So I've already installed Jupyter, so I won't be reinstalling it. Once you're done with it, run this. But before this, ensure that the location from which you're running has the meshes that you want. So the meshes that I have shared, just go to the directory where you have those meshes and type this Jupyter Notebook. I hope most of you are already familiar with Jupyter. I think it's one of the basic helping tools for Python. If not, it's basically a good GUI on top of IPython interpreter. So you can directly run functions there. So we are going to start with the loading. So once you are done with Jupyter installation, then you can simply install Conda. Using Conda, you can install IGL. Similarly, then install MeshPlot, NumPy, and SciPy. I pasted all these commands in the chat window, so you can directly check there as well. Once you're done with these installations, just run your Jupyter Notebook like I'm already running. It should open a new tab in your browser, which should look something like this. So you can basically see that you'll have something like this. So you can create a new window. You can create a new notebook with the same Python environment that you have activated right now. So once you do that, let me know. Then we'll proceed with the main library. So for till then, let's also take a look in parallel at libIGL. What libIGL is? So libIGL is actually the work of a PhD student who, during his thesis, created this library to facilitate quick prototyping. So it's essentially a C++ library, but for the sake of ease, we are going to look at the Python bindings and yeah. So libIGL is essentially one of the best libraries to quickly prototype anything that you want to do in graphics. So it has different visualization tools and functions that are pre-built into it. So we'll be taking a look at these functions today and exploring the kind of functionality that libIGL has. Yeah. Is there anyone who has any doubt? Okay. Any issues in installations? I hope not. Conda should facilitate things pretty easily. Okay, fine. So let's start with the. So firstly, what you need to do is you need to import a few things. You'll be importing IGL, you'll be importing SciPy, you'll be importing plot, subplot, and interact. So IGL is the Python binding for libIGL. SciPy is essentially a scientific Python tool library. NumPy is basically for handling the arrays, and MeshPlot is for visualization. This is another good library that we'll be using for visualizing our meshes in Jupyter. So, firstly, we are going to look at the bunny mesh. So, you can directly load it with igl.read mesh and the path to the bunny mesh. So, for example, I have the bunny mesh in my current directory. So, I'll simply say /bunny.mesh. So, when you run this, it should load the vertices, the triangles, and the faces which are available in the bunny mesh. We can also take a look at the text file to see what kind of information is being stored in the bunny mesh. In case of any doubts, just feel free to interrupt and speak. So if you open your bunny mesh in a text editor, you'll see that it is something like this. Once again, it's a simple formatted text file containing the list of vertices, specifying its dimensions. So it's a so the dimension of the vertices is 3 since it's storing the XYZ coordinate. And then comes the format of the faces. Yeah, so these are the triangles, which is basically indexing all the vertices here. So it's nothing more than a collection of vertices, triangle, and faces. So now we are going to display the face vertices and the faces and see what kind of a mesh this one is. So I've already provided you with a closed mesh. So all the holes are already filled in this one. So as to reduce the complexity of the computation that we do later on. So I've just run the plot function and pass on the vertices and the faces. So if you look at the plot function, it has different argument that it takes. So it takes vertices that are compulsory. So in case of point clouds, you can directly ignore the faces and just display the vertices. In case of triangle mesh, you also have the faces. You can plot the faces. C stands for colors. UV is the UV mapping, and similarly so on and so forth. These are different. These are the normals, the shading, and the plot, and other options that are available to you. But primarily, we are going to be only using the first three: the vertices, faces, and the colors. If I plot it using only vertices, I can visualize a point cloud. So the only difference between a point cloud and a mesh is the difference in the connectivity information. In point cloud, there is no connectivity information. It's just a set of points in 3D. But as soon as you introduce a face information, you get some structure and you can actually visualize the discrete surface. Why I'm using the word discrete here? Because it's not continuous. It's consisting of discrete triangles. So that is why I focus on the word discrete. So what are you guys able to plot it? Just add a +1 in the chat if you are able to do this. Great, great. Yeah, I'll just call up the code. Anyone who is facing any difficulty, please let me know. I'm here to take up your doubts as well. Okay. So once you're able to plot it, uh, you can actually assign colors to it as well. We'll be looking at the colors, but first let's take a look at some mesh statistics. So IGL is a wonderful library. It already has most of the things that you would want. Uh, so we'll look at the shapes first. So you can just print the shapes, and these are numpy arrays. So for example, I've printed the first three vertices and the first three faces. So these are numpy arrays, and you can take a look at the shape as well. So the just as I told you, so these are number of vertices times 3 and number of faces times 3. So now we are going to look at mesh statistics. So as I told you that there are different kinds of meshes. There are irregular meshes. The first mesh from the left is an irregular mesh because you can see that the triangles in it are non-uniform. The sizes of the triangles are non-uniform. Then towards its right, it is semi-irregular mesh or a semi-regular mesh, either way. So some of the triangles are uniform, some of the triangles are not uniform. But now if you look at the one in the rightmost section, you'll see that this is a regular mesh. All the triangles in it are uniform. So essentially, each vertex here has a six has six neighbors with each angle of 60 degrees. So it's a highly uniform mesh. And operations on such meshes offer you different computational advantages. We won't go into depth into what kind of advantages, but this is for you to know that if you get a mesh, your first attempt should be to make it a little bit more regular if you want to. You can even perform operations on irregular meshes as well. However, then the quality of the operations would vary. So you should always aim for a regular mesh. So now let's take a check at the number of irregular vertices. IGL has a function igl.isIrregularVertex. So you pass in the vertex and the faces, and it will compute the angles for you and check which of the vertices are irregular vertices. So let's so once you calculate that, we would want the count of the irregular vertices. So all you can do is just sum it up, and it will give you the count. So once you do that, we can calculate the percentage of the irregular vertices as well. So in order to do that, all you need to do is just calculate the ratio. That would be irregular vertex count divided by the vertex count. So you see that 39% of the vertices are irregular in this particular case. Are you guys able to get the statistic? Please add +1 in the chat in case you are. In case of any doubt, just feel free to ping. Okay, Devashish is able to do. What about the rest? Any doubts? Atul, Anuranjan, any doubts? Okay, great. In case of doubts, just let me know. So once you calculate the irregular vertices, you know what kind of mesh you have and what is the inherent quality of it. Similarly, there are different other properties as well. So similarly, you can calculate the area of a mesh. I'll just close this now. I'll open the other notebook that I already have. I don't have to type it again. So there are different other properties that you can check. You can check the double area. So IGL already has a function called double area. Then you can compute the min, max, and the average. And similarly, you can check the standard deviation of the areas of the triangles in the mesh. So ideally, you would want a very uniform mesh. So ideally, the area should be small in case the mesh is the dense mesh, and it should be uniform so as to avoid any irregularities in the mesh. So all these are mesh statistics that you can compute. Just quickly compute the area, average, min, max as well. So this will also be a quick revision for NumPy as well, because the best part about IGL is that it is very NumPy friendly. So you can directly pass in NumPy tensors in and out, and you can directly perform NumPy operations on it. I hope all of you are familiar with NumPy. In case you are not, it's just a library that facilitates array operations very quickly. So when you do an np.mean on the area, it will check the area vector and calculate the average for all the elements. Similarly, it will pick the min of all the elements and the max of all the elements that you have. After that, we are just calculating the sigma strand. So all these reveal some inherent properties. So like we know that 39% of the mesh is irregular. So the next thing you would want is to check the internal angle. So you can also compute the internal angles using IGL function. So internal angles are basically the angles within each triangle, within each face. So you look at this. So it's basically giving you the number of faces times all the internal angles within each face is being given. Any doubts still here? I hope this is pretty straightforward. These are just function calls that you can quickly do to evaluate what kind of mesh property you have. So what you can do now is you can take these internal angles, since these are giving you the internal angles for all the faces, and use them as colors to visualize what kind of angles are spread across the mesh.
So the whole live this library is made for triangular meshes only, or it can be extended to tetrahedras, server staging,
Yeah,
or
it can
anyone.
be extended as well. It has different operations for tetrahedral meshes as well. We are going to look at a separate library called TETGen as well, which is really helpful for the tetrahedra based operations that we want. But IGL supports tetrahedras as well. It supports point cloud, it supports meshes, and it supports different formats as well. You can go for OBJ files, PLY files, the mesh files that we are right now looking at. It's a .mesh extension. So it supports a variety of extensions.
Okay.
So now this is the kind of mesh. So this is how we can visualize the mesh angles as well. And so the darker the area, the more obtuse the angles are. The lighter the area, the more uniform they are, and so on. So you can quickly visualize this kind of structure. So the next operation comes is that we want to perform mesh decimation at times. So right now we had a small mesh, but if we take a look at an OBJ file that we earlier had, so let's load a bunny OBJ now. Instead of bunny mesh, now I'm going to read a triangle mesh. So this is a different function called bunny.obj. So now I have essentially earlier I had a mesh that had 6,000 vertices, and now I have a mesh that has 34,000 vertices. Sometimes you would want to simplify such meshes which have a large number of vertices and faces. Let's take a look at the faces as well. So right now we are somewhere around 69,000 faces. So this is a large number of mesh. And to be honest, for a single object, this is pretty decent. You can even have triangles in the order of millions in a given mesh object. Depending on the complexity of the mesh, uh, the number of triangles and vertices can increase to a great extent. So sometimes what you would want is that you would want to retain the essential properties of a given mesh while reducing the information content in it. So essentially, you would want that the bunny mesh should have lesser number of vertices and faces, but even then, it should retain the bunny-like structure. So there are different algorithms which fall into the category of mesh decimation. So essentially, given a high resolution mesh, you would want to well approximate a low resolution mesh with far fewer triangles. So one such operation is like the edge collapse. So like in this particular case, you have a set of triangles. Now what you can do with the middle two triangles that have been highlighted is that you can take the opposite edges and collapse them into a single edge. So this edge, I'll just perhaps share my notepad and show you what mesh resolution is.